In this video, I'll walk you through the router module in Bud AI Foundry. Organizations often run multiple models across on-premises infrastructure, cloud environments, or a combination of both. Each model may be optimized for a different workload, cost profile, or level of capability. That's where the router module comes in. It gives you complete control over how every request is routed across your AI deployment, ensuring it reaches the right model or agent based on the needs of your business. For example, during weekends or other periods of lower traffic, you might choose to route requests to a smaller, more cost-efficient model to reduce infrastructure costs, or you might route requests based on their intent. A legal query can be sent to a model or AI agent that's been fine-tuned on legal data, while an HR request is directed to an HR assistant, and a software engineering question goes to a coding model specialized in development tasks. You can also make routing decisions based on factors like user roles, geography, latency requirements, infrastructure availability, compliance policies, or even the current load on your deployments. Every enterprise has its own architecture, policies, and business priorities. The router module is designed to adapt to those requirements, giving you the flexibility to build routing strategies that match the way your organization operates. Now let's see how it works. Log into Bud AI Foundry and open the router module. Here you'll see all the routers that have already been configured. To create a new one, click Create Router. Start by giving your router a name and description, then select the project it belongs to and click Create Draft. You'll now be taken to the routing canvas. Think of this canvas as a visual workflow builder. Here you'll define the logic that determines how every incoming request is analyzed, evaluated, and ultimately routed to the right model or AI agent. On the right, you'll find the building blocks used to create your routing pipeline. Let's start with signals. Signals inspect every incoming request and extract information that the router can use to make decisions. For example, a keyword signal looks for specific words or phrases in the user's query. If a customer mentions terms like invoice, refund, or subscription, you can immediately route that request to the appropriate workflow. The embedding signal works differently. Instead of looking for exact keywords, it compares the incoming request against a set of reference examples using semantic similarity. For instance, you could provide a few example prompts that represent customer complaints. Even if a user doesn't use the same words, the router can recognize that the request is similar in meaning and classify it correctly. The domain signal identifies the subject area of a request, such as finance, healthcare, legal, or biology, allowing you to send it to a model that's been specialized for that domain. There are many more signals available, including language, geography, knowledge, conversation, user feedback, structure, and others. Together, they give you multiple ways to understand every incoming request before making a routing decision. Once you've identified what the request is about, the next step is the decision node. A decision defines what should happen after a signal is triggered. You can optionally add conditions, so the decision executes only when specific criteria are met. You can also assign priorities, allowing multiple decisions to be evaluated in a controlled order. For more advanced logic, you can use a rule tree. Rule trees let you combine multiple signals with logical operators before making a routing decision. For example, you might route a request only if the detected domain is legal, the language is English, and the user belongs to your enterprise tier. This allows you to build sophisticated routing policies without writing code. Once the decision is satisfied, you add one or more endpoints. Endpoints represent the models or AI agents that will process the request. A decision can have a single endpoint or multiple endpoints, depending on how you want requests to be handled. Next is an optional component called projection. Most routers won't need it. Some signals simply return a category, while others produce a continuous value, such as a confidence score. Projection transforms that value into a form that's easier for decisions to work with. Several projection types are available. Partition projection groups related signals into named buckets and ensures only one category is selected for each request. Score projection combines multiple signals into a single weighted score. For example, you could estimate request complexity by combining factors like prompt length, presence of code, and reasoning depth. Mapping projection converts numeric scores into meaningful labels that can be referenced by your routing logic. Once you've configured your endpoints, the next step is choosing how the router selects between them. Bud AI Foundry offers several routing algorithms. Confidence Looper starts with a smaller, more cost-effective model and only escalates to larger models if the response doesn't meet the required confidence threshold. This is an effective way to reduce inference costs while maintaining response quality. Ratings Looper sends the request to multiple models in parallel and returns the response with the highest quality score. This is ideal when answer quality matters more than cost. Reasoning Mixture performs multiple rounds of reasoning across models and synthesizes a final response, making it well-suited for complex reasoning tasks. If you don't need iterative evaluation, you can use one of the selection algorithms instead. Static selection always chooses the first endpoint, making it ideal for deterministic routing. Router DC automatically selects the model whose capabilities best match the incoming request. For example, it might choose one model for coding tasks, another for legal questions, and another for creative writing. AutoMix first attempts the request with a smaller model and escalates only if the response fails verification, giving you a good balance between quality and cost. Additional strategies include latency-aware selection, round robin, least busy, random, and several others to suit different deployment requirements. The final layer of the routing pipeline is plugins. Plugins apply additional behavior after an endpoint has been selected. Semantic cache serves semantically similar requests directly from cache, reducing latency and inference costs. System prompt override dynamically replaces the system prompt for a request. Request parameter override modifies request parameters before they're sent to the model. And fast response provides a predefined fallback response whenever no routing condition is satisfied. So, to summarize, signals understand the request. Decisions determine where it should go. Endpoints process it. Algorithms decide which endpoint to use, and plugins enhance the request before or after it reaches the model. Once your router is ready, publish it. From the associated project, open the Routers tab to view all deployed routers. From here, you can copy the integration snippet and use it directly in your applications. The Analytics tab provides detailed insights into traffic, routing behavior, endpoint usage, latency, and overall performance. And that's a quick tour of the router module in Bud AI Foundry. It gives you complete control over how AI requests flow through your infrastructure, helping you optimize cost, improve performance, enforce business policies, and ensure every request reaches the model or agent that's best suited to handle it. Want to see how Bud AI Foundry can support your AI deployment? Contact us for a personalized demo.